This presentation is delivered by the Stanford Center for Professional Development.
Oh, good. We got volume and everything. All right, here we go. Lest you think you're learning things that aren't going to actually someday help you in your future career. Let's say you plan to be president. You think, should I take 106b? Should I not take 106b? Watch this interview and you will see.
We have questions, and we ask our candidates questions. And this one is from Larry Schwimmer. Okay. What? You guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no. I think
that's not a.
I think the bubble sort would be the wrong way to go.
Come on, who told him this?
Okay. There you go. So apparently, and the question was actually by a former student of mine, in fact, Larry Schwimmer. So apparently he's been prepped well. As part of going on the campaign trail, not only do you have to know all your policy statements, you also have to have your n squared and log n sorts kept straight in your mind. So just so you know. So let me give you some examples of things that are graphs, just to get you thinking about the data structure that we're going to be working with and playing around with today. That sometimes you think of graphs as being those like bar graphs, right? You're graphing histograms. This is actually a different kind of graph. The computer scientist form of graph is just a generalized recursive data structure that kind of starts with something that looks a little bit like a tree and extends it to this notion that there are any number of nodes. In this case represented as the cities in this airline route map. And then there are connections between them, sometimes called edges or arcs, that wire up the connections that in the case, for example, of this graph are showing you which cities have connecting flights. You have a direct flight that takes you from Las Vegas to Phoenix, right? One from Phoenix to Oklahoma City. There's not a direct flight from Phoenix to Kansas City, but there's a path by which you could get there by taking a sequence of connecting flights, right? Going from Phoenix to Oklahoma City to Kansas City is one way to get there. And so the entire kind of map of airline routes forms a graph, right, of the city. And there are a lot of interesting questions that, having represented that data, you might want to answer about finding flights, that are cheap or meet your time specification or get you where you want to go. And that this data would be kind of primary in solving that problem. Another one, right, another idea of something that's represented as a graph is something that would support the notion of word ladders, those little puzzles where you're given the word cord and you want to change it into the word worm, and you have these rules that say, well, you can change one letter at a time. And so the connections in the case of the word ladder have to do with words that are one character different from their neighbors, have direct connections or arcs between them. Each of the nodes themselves represents a word, and then paths between that represent word ladders, that if you can go from here through a sequence of steps directly connecting your way, each of those stepping stones is a word in the chain that makes a word ladder. So things you might want to solve there is, what's the shortest word ladder? How many different word ladders, how many different ways can I go from this word to that one, right? Could be answered by searching around in a space like this. Any kind of prerequisite structure, such as the one for the major that might say you need to take this class before you take that class and this class before that class, right, forms a structure that also fits into the name graph. In this case, there's a connection to those arcs, that the prerequisite is such that you take 106A and it leads into 106B, and that connection doesn't really go in the reverse, right? You don't start in 106B and move backwards. Whereas in the case, for example, of the word ladder, all of these arcs are what we call undirected. Right, you can traverse, from wood to word and back again, right? They're equally visitable, or neighbors in this case. So there may be a situation where we have directed arcs where they really imply a one-way directionality through the paths. Another one, lots and lots of arrows, that tell you about the life cycle of Stanford relationships, all captured on one slide. In terms of flowcharts. So flowcharts have a lot of things about directionality, like you're in this state and you can move to this state, so that's your neighboring state, and the arcs in there connect those things. And so as you will see, like you get to start over here and like be single and love it, right? And then you can kind of flirt with various degrees of seriousness, right? And then eventually there involves a trombone serenade, which, you can't go back to flirting aimlessly after the trombone serenade. There's no arc that direction. When somebody gets the trombone out, you either take them seriously or you completely blow them off. There's the back there. And then there's dating, and then there's two-phase commit, which is a very important part of any computer scientist education. And then potentially, other tracks of children and whatnot. But it does show you kind of places you can go, right? It turns out you actually don't get to go from flirt aimlessly to have baby. So write that down. Not allowed in this graph. And then it turns out some things you've already seen are actually graphs in disguise. I didn't tell you when I gave you the maze problem and its solution, the solving and building of a maze, that in fact what you're working on though is something that is a graph, that a perfect maze, right? So we started with this fully disconnected maze. If you remember how the Aldous-Broder algorithm worked, it's like you have all these nodes that have no connections between them. And then you went bopping around, breaking down walls, which is effectively connecting up the nodes to each other. And we kept doing that until actually all of the nodes were connected. So in effect, we were building a graph out of this big grid of cells by knocking down those walls to build the connections. And when we were done, then we made it so that it was possible to trace paths starting from that lower corner and working our way through the neighbors all the way over to there. So in the case of this, if you imagine that each of these cells was broken out in this little thing, there'd be these neighboring connections where this guy has this neighbor but no other ones, because actually it has no other directions you can move from there, but some of them, for example, like this one, has a full set of 4 neighbors you can reach, depending on which walls are intact or not. And so the creation of that, right, was creating a graph out of a set of disconnected nodes, and then solving it is searching that graph for a path. So let's talk like concretely. How are we going to make stuff work on graphs? Graphs turn out to actually, by showing you that, I'm trying to get you this idea that a lot of things are really just graphs in disguise. That a lot of the problems you may want to solve, if you can represent it as a graph, then things you learn about how to manipulate graphs will help you to solve that kind of problem. So the basic idea of a graph, it is a recursive data structure based on the node, where nodes have connections to other nodes. Okay, so that's kind of like a tree, but it actually is more freeform than a tree, right? In a tree, right, there's that single root node that has kind of a special place, and there's this restriction about the connections, that there's a single path from every other node in the tree, starting from the root that leads to it. So you never can get there by multiple ways, and there's no cycles, right? And it's all connected and things like that. So in terms of a graph, it just doesn't place those restrictions. It says there's a node, it has any number of pointers to other nodes. It potentially could even have 0 pointers to other nodes. So it could be a little island of its own out here that has no incoming or outgoing flights, right? You have to swim if you want to get there. And then there's also not a rule that says that you can't have multiple ways to get to the same node. So if you're at B and you're interested in getting to C, you could take the direct connection here, but you could also take a longer path that bops through A and hits to C. And so there's more than one way to get there, which would not be true in a tree structure where it has that constraint. But that adds some interesting challenges to solving problems in the graphs, because there actually are so many different ways you can get to the same place. We have to be careful about avoiding getting into circularities where we're doing that, and also not redundantly doing work we've already done before because we've visited it previously. There can be cycles where you can completely come around. I think this one actually doesn't have a cycle in it. No, it doesn't. But if I could add a link, for example, from C back to B, and then there would be this place you could just kind of keep rolling around in the BAC area. So we call each of those guys, the circles here, the nodes, right? The connections between them, arcs. We will talk about the arcs as being directed and undirected in different situations where we imply that there's a directionality. You can travel the arc only one way, or in cases where it's undirected, it means it goes up both ways. We'll talk about 2 nodes being connected, meaning there is a direct connection, an arc between them. And if they're not directly connected, there may possibly be a path between them. A sequence of arcs forms a path that you can follow to get from one node to another. And then cycles just meaning a path that revisits one of the nodes that was previously traveled on that path. So I've got a little terminology. Let's talk a little bit about how we're going to represent it. So before we start making stuff happen on them, it's like, well, how's this in C++, right? What's the best way, or what are the reasonable ways you might represent this kind of connected structure? So if I have this 4-node graph, A, B, C, D over here, with the connections that are shown with direction, in this case I have directed arcs, that one way to think of it is that what a graph really is a set of nodes and a set of arcs. And by set, I mean sort of just a generalization. There might be a vector of arcs, there might be a vector of nodes, whatever, but some collection of arcs, some collection of nodes. And that the nodes might have information about, what location they represent or what word or what entity, in a social network that they are. And then the arcs would show who's directly connected to whom. And so one way to manage that, right, is to just have two independent collections, a collection of nodes and a collection of arcs. And that when I need to know things about connections, I'll have to kind of use both in tandem. So if I want to know if A is connected to B, I might actually have to just walk through the entire set of arcs trying to find one that connects A and B as its endpoints. If I want to see if C is connected to B, same thing, just walk down the whole set. That's probably the simplest thing to do, right, is to just kind of have them just be maintained as the two things that are used in conjunction. More likely, what you're going to want to do is provide some access that when at a current node, you're currently trying to do some processing from the node B, it would be convenient if you could easily access those nodes that emanate or outgo from the B node. That's typically the thing you're trying to do is at B, try to visit its neighbors. And rather than having to kind of pluck them out of the entire collection, it might be handy if they were already kind of stored in such a way to make it easy for you to get to that. So the two ways that try to represent adjacency in a more efficient way are the adjacency list and the adjacency matrix. So in an adjacency list representation, we have a way of associating with each node, probably just by storing it in the node structure itself, those arcs that outgo from there. So in this case, A has a direct connection to the B and C nodes, and so I would have that information stored with the A node, which is my vector or set of outgoing connections. Similarly, B has one outgoing connection which goes to D, C has an outgoing connection to D, and then D has outgoing connections that lead back to A and to B. So at a particular node, I could say, well, who's my neighbors? It would be easily accessible and not have to be retrieved or searched or filtered. Another way of doing that, right, is to realize that in a sense what we have is this kind of n by n grid where each node is potentially connected to the other n-1 nodes in that graph. And so if I just build a 2 by 2 matrix that's labeled with all the node names on this side and all the node names across the top, that the intersection of this is there an arc that leads away from A and ends at B? Yes, there is. Is there one from A to C? And then the places where there is not an existing connection, a self loop or just a connection that doesn't exist, right? I have an empty slot. So maybe these would be Booleans, true and false or something, or maybe there'd be some more information here about the distance or other associated arc properties for that particular connection. In this case, it's actually very easy then to actually do the really quick search of I'm at A and I want to know if I can get to B. Then it's really just a matter of reaching right into the slot in constant time in that matrix, right, to pull it out. And so this one involves a lot of searching to find things. This one involves maybe perhaps a little bit of searching. If I want to know if A is connected to B, I might have to look through all its outgoing connections, right? This one gives me that direct access. But the trade-offs here has to do with where the space starts building up, right? A full n by n matrix could be very big, right? In some sense, we're allocating space as though there are a full set of connections between all the nodes, every node connected to every other. And in the cases where a lot of those things are false, right, there's a lot of capacity that we have set aside that we're not really tapping into. And so in the case of a graph that we call dense, where there's a lot of connections, it will use a lot of that capacity and might make sense. In a graph that's more sparse, where there's a few connections, so you have thousands of nodes, but maybe only 3 or 4 on average are connected to one, then having allocated 1,000 slots of which to only fill in 3 might become rather space inefficient. You might prefer an adjacency list representation that can get you to the ones you're actually using and versus the other. But in terms of the adjacency matrix, it's very fast, right? A lot of space thrown at this gives you this immediate O1 access to know who your neighbors are. So we're going to use the adjacency list kind of strategy here for the code we're going to do today, and it's just it's a kind of a good compromise between the two alternatives that we've seen there. So I have a struct node. It has some information for the node. Given that I'm not being very specific about what the graph is, I'm just going to kind of leave that unspecified. It might be that it's the city name, it might be that it's a word, it might be that it's a person in a social network, some information that represents, what this node is as an entity. And then there's going to be a set of arcs or a set of nodes it's connected to. And so I'm using vector here. I could be using set. I could be using, a raw array or a linked list or any of these things. I need to use some unbounded collection though, because there's no guarantee that there will be 0 or 1 or 2 the way there is in a linked list or a tree where there's a specified number of outgoing links. There can be any number of them, so I'm just leaving a variable size collection here to do that work for me. The graph itself, so I have this idea of all the nodes in the graph, right, would each get a new node structure and then be wired up to the other nodes that they are connected to. But then when I'm trying to operate on that graph, I can't just take one pointer and say, here's a pointer to some node in the graph and say, this is, and from here, you have access to everything. And the way that a tree, the only thing we need to keep track of is the pointer to the root. Or a linked list, the only thing we keep a pointer to typically is that frontmost cell. And from there, we can reach everything else. There is no special head or root cell in a graph. A graph is this kind of crazy collection, right, without a lot of rules about how they are connected. In fact, it's not even guaranteed that they totally are connected. That I can't guarantee that if I had a pointer, for example, to C, right, I may or may not be able to reach all the nodes from there. If I had a pointer to A, right, A can get to C and B and then also down to D. But for example, there could just be an E node over here that was only connected to C or not connected to anything at all for that matter, connected to F in their own little island. That there is no way to identify some special node from which you could reach all the nodes. There isn't a special root node, and you can't even just arbitrarily pick one to be the root, because actually there's no guarantee that it will be connected to all of the others. So it would not give you access to the full entirety of your graph if you just picked one and said, well, anything reachable from here, it might not get you the whole thing. So typically what you need to really operate on is the entire collection of node stars. You'll have a set or a vector that contains all the nodes that are in the graph. And then within that, there's a bunch of other connections, right, that are being made on the graph connectivity that you're also exploring. So let's make it a little bit more concrete and talk a little bit about, well, what really is a node? What really is an arc? There may actually be some more information I need to store than just a node is connected to other nodes. So in the case of a list or a tree, the next field and the left and the right field are really just pointers for the purpose of organization. You know, that's the pointer to the next cell. There's no data that is really associated with that link itself. That's not true in the case of a graph. That often what the links that connect up the nodes actually do have a real role to play in terms of being data. It may be that what they tell you is what road you're taking here, or how long this path is, or how much this flight costs, or what time this flight leaves, or how full this flight already is, or who knows, you know, just other information that is more than just this node's connected to that one. It's like, how is it connected? What is it connected by? And what are the details of how that connection is being represented? So it's likely that what you really want is not just pointers to other nodes, but information about that actual link stored with an arc structure. So typically we're going to have an arc which has information about that arc, how long, how much it costs, you know, what flight number it is, that will have pointers to the start and end node that it is connecting. The node then has a collection of arcs, and those arcs are expected to, in the adjacency list form, will all be arcs that start at this node, so their start node is equal to the one that's holding on to them, and then they have an end pointer that points to the node at the other end of the arc. Well, this gets us into a little bit of a C++ bind, because I've described these data structures in a way that they both depend on each other, that an arc has pointers to the start and the end node. A node has a collection of arcs, which is probably a vector array set of arc pointers. And so I'm starting to define the structure for arc, and then I want to talk about node in it. And I think, oh, okay, well then I better define node first, because C++ always likes to see things in order. Remember, it always wants to see A and then B if B uses A. And so in terms of how your functions and data structures work, you've always gotten this idea of like, well, go do the one first. Well, if I say, okay, arc's going to need node, I start to write arc, and I say, oh, I need to talk about node. Well, I better put node up here, right? But then when I'm starting to write node, I start talking about arc. And they have a circular reference to each other, right? They both want to depend on the other one before we've gotten around to telling the compiler about it. One of them has to go first, right? What are we going to do? What we need to do is use the C++ forward reference as a little hint to the compiler that we are going to be defining a node T structure in a little bit. We're going to get to it, but first we're going to define the arc T structure that uses that node T, and then we're going to get around to it. So we're going to give it like a little heads up that says, there later will be, you know, in Act 2 of this play, we're going to introduce a character called node T. So you can now start talking about node T in some simple ways based on your agreement to the compiler that you plan on telling it more about node T later. So the struct node T says, there will be a struct called node T. Okay, the compiler says, okay, I'll write that down. You start defining struct argt, and it says, oh, I see you have these pointers to the node T. Okay, well, you told me there'd be a struct like that. I guess that'll work out. And now you told it what struct node T is. It's like, oh, I have pointers, a vector with these pointers to arcs. And then it says, okay, now I see the whole picture. And it all worked out. So it's just a little bit of a requirement of how the C++ compiler likes to see stuff in order without ever having to go backwards to check anything out again. So I got myself some node structures, got some arc structures. They're all working together. I'm going to try to do some traversals, try to do some operations that work their way around the graph. So tree traversals, right, the pre and post in order, are ways that you start at the root and you visit all the nodes in the tree. Very common need to kind of process, to delete nodes, to print the nodes, to whatnot. So we might want to do the same thing on graphs. I've got a graph out there and I'd like to go exploring it. Maybe I just want to print that if I'm in the Gates building, what are all the places that I can reach from the Gates building? Where can I go to? What options do I have? What I'm going to do is a traversal starting at a node and kind of working my way outward to the visible, reachable nodes that I can follow those paths to get there. We're going to look at two different ways to do this. One is depth first and one is breadth first. And I'll show you both algorithms, and they will visit the same nodes. When all is done and said, they will visit all the reachable nodes starting from a position, but they will visit them in different order. So just like the pre, post, in order tree traversals, they visit all the same nodes. It's just a matter of when they get around to doing it, is how we distinguish depth and breadth first traversals. Because we have this graph structure that has this loose connectivity and the possibility of cycles and multiple paths to the same node, we are going to have to be a little bit careful in how we do our work to make sure that we don't end up getting stuck in some infinite loop when we keep going around the ABC cycle in a particular graph. That we need to realize when we're revisiting something we've seen before and then not trigger kind of an exploration we've already done. So let's look at depth first. This is probably the simpler of the two. They're both actually pretty simple. Depth first traversal uses recursion to do its work. And the idea is that you pick a starting node. Let's say I want to start at Gates, and that maybe what I'm trying to find is all the reachable nodes from Gates. If I don't have a starting node, then I can just pick one arbitrarily from the graph because there is actually no root node, right, of special status. And the idea is to go deep. That in the case of, for example, a maze, it might be that I choose to go north and then I just keep going north. I just go north until I run into a dead wall, and then I say, oh, I have to go east. I'm going to go east. The idea is to just go as far away from the original state as I can. Just keep going outward. And eventually I'm going to run into some dead end. And that dead end could be I get to a node that has no outgoing arcs. Or it could be that I get to a node whose only arcs come back to places I've already been. So cycle back on itself, in which case that also is really a dead end. So you go deep. You go north and you see as far as you can get. And only after you've kind of fully explored everything reachable from starting in the north direction do you backtrack, unmake that decision and say, well, how about not north, how about east, right? And then find everything you can get to from the east. And after kind of going all through that, come back and try south and so on. So all the options you have, exhaustively getting through all your neighbors in this kind of go deep strategy. One of the important things is to realize if you've got this recursion going, so what you're actually doing is basically saying, I'm going to step to my neighbor to the right and I'm going to explore all the things, so do a depth first search from there to find all the places you can reach. And that one says, well, I'm going to step through this spot and go to one of my neighbors. And so we can't do that infinitely without getting into trouble. We need to have a base case that stops that recursion. And the two cases that I've already talked about, one is just, well, when you have no neighbors left to go. So when you are get to a node that actually kind of is a dead end, or that neighbor only has visited neighbors that surround it. So a very simple little piece of code that depends on recursion doing its job. In this case, right, we need to know which nodes we have visited. Right? We're going to have some kind of strategy for saying, I have been here before. In this case, I'm using just a set, because that's an easy thing to do. I make a set of node pointers, and I update it each time I see a new node. I add it to that set, and if I ever get to a node who was already previously visited, right, then there's no reason to do any work from there. We can immediately stop. So starting that step would be empty. If the visit already contains the node that we're currently trying to visit, then there's nothing to do. Otherwise, we go ahead and add it, and there's a little note that says, we'll do something with cur. What am I trying to do here? Am I trying to print those nodes? Am I trying to draw pictures on those nodes, highlight those nodes? You know, something I'm doing with them. I don't know what it is, but this is the structure for the depth first search here. And then for all of the neighbors, using the vector of outgoing connections, then I run a depth first search on each of those neighbors, passing that visited set by reference through the whole operation. So I will always be adding to and modifying this one set. So I will be able to know where I've been and where I still need to go. So if we trace this guy in action, if I start from arbitrarily from A, I say I'd like to begin with A, then the depth first search is going to pick a neighbor, and let's say I happen to just work over my neighbors in alphabetical order, and would say, okay, well, I've picked B. Let's go to everywhere we can get to from B. So A gets marked as visited. I move on to B. I say, well, B, search everywhere you can get to from B. And B says, okay, well, I need to pick a neighbor. How about I pick C? It says everywhere. It says, and now, having visited C, go everywhere you can get to from C. Well, C has no neighbors. Right, no outgoing connections whatsoever. So C says, well, okay, that's everywhere you can get to from C is C. You know, I'm done. That will cause it to backtrack to this place, to B, and B says, okay, I explored everywhere I can get to from C. What other neighbors do I have? B has no other neighbors. So in fact, B backtracks all the way back to A. So now A says, okay, well, I went everywhere I can get to from B, right? Let me look at my next neighbor. My next neighbor is C. But C already visited, so there's no reason to go crazy on that thing. So in fact, I can immediately see that I visited that, so I don't have any further path to look at there. I'll hit D then as the next one in sequence. So at this point, I've done everything reachable from the B arm, everything reachable from the C arm, and now I'm starting on the D arm. I say, okay, where can I get to from D? Well, I can get to E. Right, where can I get to from E? E goes to F. So the idea is you think of it going deep. It's going as far away as it can, as deep as possible before it kind of unwinds, getting to the F that has no neighbors, and saying, okay, well, how about where can I get to? Also from E, I can get to G. From G, where can I get to? Nowhere. And so we kind of unwind the D arm, and then we will eventually get back to and hit the H. So the order they actually were hit in this case happened to be alphabetical. I assigned them such that that would come out that way. That's not really a property of what depth first search does. But think of it as like it's going as deep as possible, as far away as possible. And so it makes a choice. It's very much like the recursive backtrackers that we've seen. In fact, they make a choice, commit to it, and just move forward on it, right? Never kind of giving a backwards glance. And only if the whole process, right, bottoms out, does it come back and start unmaking decisions and try alternatives, eventually exploring everything reachable from A when all is done and said. So if you, for example, use that on the maze, right, the depth first search on a maze is very much the same strategy we're talking about here. If you, instead of the way we did it was actually breadth first search, if you remember back to that assignment, the depth first search alternative is actually doing it with the just go deep. Make a choice, go with it, run all the way until it bottoms out, and only then back up and try some other alternatives. The breadth first traversal. Going to hit the same nodes, but just going to hit them in a different way. If my goal were to actually hit all of them, right, then either of them is going to be a fine strategy. There may be some reason why I'm hoping to stop the search early, and that actually might dictate why I would prefer which ones to look at first. The breadth first traversal is going to explore things in terms of distance, in this case expressed in terms of number of hops away from the starting node. So it's going to look at everything that's 1 hop away, and then go back and look at everything 2 hops away, and then 3 hops away. And so if the goal, for example, was to find a node in a shortest path connection between it, then breadth first search by looking at all the ones 1 hop away, if it was a 1 hop path, it'll find it. And if it's a 2 hop path, it'll find it on that next round, and then the 3 hop path. And there might be paths that are 10 and 20 and 100 steps long, but if I find it earlier, I won't go looking at them. It actually might prove to be a more efficient way to get to the shortest solution, as opposed to depth first search, which would go off and try all these deep paths that may not ever end up where I want it to be before it eventually made its way to the short solution I was wanting to find. So the idea is we have the starting node. We're going to visit all the immediate neighbors. so basically a loop over the immediate one. And then while we're doing that, we're going to actually kind of be gathering up that next generation. Sometimes that's called the frontier, sort of advancing the frontier of the nodes to explore next. So all the nodes that are 2 hops away. And then while we're processing the ones that are 2 hops away, we're going to be gathering the frontier that is 3 hops away. And so at each stage, right, we'll be kind of processing a generation, but while assembling the generation n+1 in case we need to go further to find those things. We'll use an auxiliary data structure during this, right? That management of the frontier, keeping track of the nodes that are kind of staged for the subsequent iterations. The queue is a perfect data structure for that. If I put the initial neighbors into a queue, as I dequeue them, if I put their neighbors on the back of the queue, so enqueue them behind all the 1-hop neighbors, then if I do that, we've got as I'm processing generation 1 off the front of the queue, I'll be stacking generation 2 in the back of the queue. And then when all of generation 1 is exhausted, I'll be processing generation 2, but kind of enqueuing generation 3 behind it. Same deal that we had with depth first search, though, is we will have to be careful about cycles, multiple paths, that when there's more than one possibility of how we get to something, we don't want to kind of keep going around that cycle or do a lot of redundant work visiting nodes that we've already seen. So I have the same idea of keeping a track of a set that knows what we've previously visited. And the initial node gets enqueued, it's kind of by itself, so this is like generation 0 gets put into the queue, and then while the queue is not empty, so while there's still neighbors I haven't yet visited, I dequeue the frontmost one. If it hasn't already been visited on some previous iteration, then I mark it as visited, and then I enqueue all of its children or neighbors at the back of the queue. And so if right now I'm processing generation 0, that means all of generation 1, so the neighbors that are 1 hop away, get placed in the queue. And then the next iteration coming around here will pull off a generation 1 and then enqueue all of these 2-hop neighbors, come back, and other generation 1s will get pulled off, enqueue their 2-hop neighbors, and so the 2-hop generation will kind of be built up behind, and then once the last of the 1-hop generation gets managed, we'll start processing the generation 2 and so on. And so this will keep going, right, while the queue has some contents in there, so that means some neighbors, right, we have connections to that we haven't yet had a chance to explore, and either we will find out that they have all been visited, so this will end when all of the nodes, right, that are in the queue have been visited, right, or there are no more neighbors to enqueue. So we've gotten to those dead ends or those cycles that mean we've reached everything that was reachable from that start node. You okay with that? And so I traced this guy to see it doing its work. So if I start again with A, and again, assuming that I'm going to process my nodes in alphabetical order when I have children. So I will go through and I will enqueue. So the queue right now has just node A in it. I pull it off. I say, have I visited? No, I have not. So then I mark it as visited. And now for each of its neighboring nodes, B, C, D, H, I'm going to put those into the queue. And so then they're loaded up. And then I come back around and I say, do I still have stuff in the queue? I do. So let's take out the first thing that was put in. It was B. Okay, and I'll say, okay, well, where can you get to from B? You can get to C, so I'm going to put C in the queue. Now, C is actually already in the queue, but we're going to pull it out earlier, so in terms it'll get handled by the visiting status later. So it'll say, okay, we'll put C, D, and E in, and then put C behind it. So right now we'll have C, D, H, and C again. It'll find the C that's in the front there. It'll say, where can you get to from C? Nowhere. So no additional generation 2s are added by that one. I'll look at D and I'll say, okay, well, what generation 2s do we have from D? It says, well, I can get to E, right? So put E on the back of the queue. Look at H. Where can H get to? H can get to G. So go ahead and put G on the back of the queue. So now it comes back around to the things that are 2 hops away. The first one it's going to pull off is C. It's going to say, well, C is already visited. So there's no need to redundantly visit that or do anything with that. It passes over C. It finds the E that's behind that. And then it finds the G that was behind the H. The E also enqueued the F that was 4 hops, and the very last one, right, output will be that F that was only reachable by taking, 3 hops away from the thing. So this one's kind of working radially, right? The idea that I'm looking at all the things that I can get to kind of in 1 hop are my first generation, then 2 hops, then 3 hops. And so it's like throwing a stone into water and watching it ripple out. that the visiting, right, is managed in terms of kind of growing length of path, right, number of hops that it took to get there. So this is the strategy that you used for maze solving, if you remember, that what you were tracking, right, was this queue of paths where the path was, AB or ABC or ADE, and then they grew stepwise at kind of each iteration through the traversal there, where you're saying, okay, well, I've seen all the paths that are 1 hop, now I've seen all the ones 2, now the ones 3 and 4 and 5. And when you keep doing that, eventually you get to the hop, 75, which leads you all the way to the goal. And since you have looked at all the paths that were 74 and shorter, that the first path that you DQ that leads to your goal must be the best or the shortest overall, because because of the order you process them. That's not true in depth first search, right? That depth first search might find a much longer and more circuitous path that led to the goal when there is a shorter one that would be eventually found. If I had a graph that looked, had this long path, let's say, and so this is the goal node, let's say, and this is the start node, that there could be a 2-hop path kind of off to this angle, but if this was the first one explored in the depth first, right, it could eventually kind of work its way all the way around through this 8-hop path and say, okay, well, I found it, right? It would be the first one we found, but there's no guarantee that would be the shortest in depth first search, right? It would just happen to be the one that, based on its arbitrary choice of which neighbors to pursue it happened to get to, that there could be a shorter one that would be found later in the traversal. That's not true, right, in the breadth first search strategy, because it will be looking at this and then these two and then these two and kind of working its way outward down those edges. So as soon as we get to one that hits the goal, we know we have found the shortest we could have. Question?
I was wondering, in that case, you could return, okay, we need 2 jumps to get to the goal, like the shortest way to the goal. How do we remember which path led us there?
So probably so if you were really doing that, in terms of depth first search, what you'd probably be tracking is what's the path, probably a stack that said, here's the stack that led to that path. Let me hold on to this, right? And I will compare it to these alternatives. So I'll try out on neighbor 1, get the stack back from that's the best. Try it on neighbor 2, get that stack back, see which one is smaller, right, and use that as the better choice. And so eventually when I tried it out this side, I'd get this stack back that was just 2, and I could say, yeah, that was better than this 10-step path I had over here, so I will prefer that. So just using your standard kind of backtracking with using your return values, incorporating them, deciding which was better. And so in this case, right, the depth first search, right, can't really be pruned very easily, right? Because it has to kind of explore the whole thing to know, right, that this short little path right over here happened to be just arbitrarily examined last. Whereas the breadth first search actually does kind of, because it's prioritizing by order of length, if the goal was shortest path, it will find it sooner and be able to stop when it found it, rather than look at these longer paths. So it won't end up, if there were hundreds of other paths over here, right, breadth first search won't actually have to ever reach them or explore them. So there are a lot of things that actually end up being graph search in disguise. That's why kind of a graph is a great data structure to kind of get to in 106b, because there are lots of problems that in the end, if you can model them using the same setup of nodes and arcs and traversals, right, that you can answer interesting questions about that data by applying the same graph search techniques. So sometimes you want to know things like, well, which nodes are reachable from this node at all? And then that just means, okay, I'm here and I want to get to these places. What places could I get to? Or knowing what courses I could take, right, that would, lead me to a CS degree is kind of like, well, looking for the ones that lead to having all your graduation requirements, satisfied. And each of those arcs could be a course you could take, right? How close does that get you to the goal? How can I get to the place I'd like to be? Or what are the places that this course, right, satisfies requirements that lead to? Knowing things about connectivity is kind of useful in things like the kind of Bacon numbers or Erdős numbers, where people want to know, well, how close am I to greatness have I been in a movie with someone who was in a movie with Kevin Bacon? And for me, it turns out 0. I haven't been in no movies, but have you written a paper with someone who then connects through a chain to some other famous person, right? Tells you about your kind of social network distance or something. Or in LinkedIn, you're trying to get a new job and you want to find somebody to introduce you to the head of this cool company. It's like figuring out who you know who knows them, right? Is finding paths right through a social network graph. Finding out things like, well, are there paths with cycles? What's the shortest path to the cycle, longest path to the cycle? Often tells you things about redundancies in that structure. That, for example, when you're building a network infrastructure, sometimes you do have cycles in it because you actually want to have multiple ways to get to things in case there's a breakdown. Like if there's a freeway accident, you want to have another way to get around it. But you are interested in maybe trying to keep your costs down, is trying to find out where the right places to put in those redundancies, those cycles that give you the best benefit, right, with the least cost. Trying to find things like a continuous path that visits all the nodes once and exactly once, especially doing so efficiently, picking a short overall path for that. We talked a little bit about that in terms of what's called the traveling salesman problem. You are trying to get from, you have 10 cities to visit on your book tour, you don't want to spend all your lifetime on a plane. What's the path, right, of crisscrossing the country that gets you to all 10 of those with the least time painfully spent on an airline? And so those are just graph search problems. You have these nodes, you have these arcs, right? How can you traverse them and visit, right? And come up with a good solution. There's other problems that I think that are kind of neat. Word letters, we used to give out an assignment on word letters. We didn't this time, but I thought it was an interesting problem to think about, right? The idea of how it is you can transform one letter at a time, right, from one word to another, right, is very much a graph problem behind the scenes, right? And that largely a breadth-first traversal is exactly what you're looking for there. How can I transform this with the shortest number of steps is kind of working radially out from the starting word. Your Boggle board turns out really is just a graph. If you think of having this sequence of letters that you're trying to work through, that really each of these letters can actually just be thought of as a node, and then the connections it has are to its 8 neighbors. And that finding words in there is basically finding paths starting from this node, right, that lead away, that don't revisit, right? So in fact, doing breadth first or depth first search, you most likely did depth first search when you were writing the implementation of Boggle, that does kind of a deep search on I found an A, I found a P, I found a P, and kind of keeps going as long as that path looks viable. So in this case, that the arc information we're using is having assembled those letters, do they form a prefix that could be leading somewhere good? And then the kind of recursion bottoming out when we have run ourselves into a corner where we have no unvisited nodes that neighbor us, or only nodes that would extend to a prefix that no longer forms any viable words, as a search problem. So it feels like everything you've done this quarter has actually been a graph in disguise. I just didn't tell you, right? The maze problem, right, is very much a graph search problem, building a graph and searching it. Another one that I think is kind of neat to think about is kind of related to the idea of word ladders, is that often when you mistype a word, a word processor will suggest to you, here's a word that you might have meant instead. You type a word that it doesn't have in its lexicon, and it says, well, that could just be, a word I don't know, but it also could mean that you actually mistyped something. And so what you want to look at is having neighboring nodes, sort of diagramming a graph of all the words you know of, and then the kind of permutations, the tiny little twiddles to that word that are neighbors to it, right? So that you could describe a set of suggestions, right, as being those things that are within a certain hop distance from the original mistyped word. And so you could say, yeah, things that have 2 letters different are probably close enough, but things that have 3 or more letters different aren't actually likely to be the mistyped word. And then that kind of leads to supporting things like wildcard searches, where you're trying to remember whether it's E-R-A-T or A-R-T-E at the end of desperate, that those things can be modeled as kind of like a search through a graph space where you're modeling those letters, and then there's like a branching where you try all of the letters coming out of D-E-S-P, seeing if any of them lead to an R-A-T-E. So the last thing I wanted to just bring up, and this is the one that's going into this week's assignment, I'm just going to actually show it to you to kind of get you thinking about it, because it's actually the problem at hand that you're going to be solving, is that the one of where I'm interested in finding this shortest path, but I'm going to add in this new idea that all hops are not created equal. That a flight from San Francisco to Seattle, right, is a shorter distance, right, than the one that goes from San Francisco to Boston. And if I'm interested in getting to some place, it's not just that I'd like to take a direct flight. I'd also like to take the set of flights that involves the least kind of going out of my way and going through other cities and in other directions. And so in this case, right, a breadth first search is a little bit too simplistic. That if I just look at all the places I can get to in one hop, that those are not really equally weighted in terms of my goal of minimizing my total path distance. But if I instead prioritize should in your mind immediately conjure up images of the priority queue, to look at paths that are, if I'm trying to minimize total distance, the shortest path, right? Even if they represent several hops, if they're still shorter, if I have 3 flights that each are 100 miles, then they represent a flight of 300 total miles. And that's still preferred to one that actually is 2,000 miles or 7,000 miles going to Asia, alternatively. And so if I worked on a breadth first that's been modified by total distance, that it would be a way to work out the shortest path, right, in terms of total weight from San Francisco to my destination by a modified breadth first kind of weighted strategy. And that is exactly what you're going to be doing in this assignment. I'm not going to give away too much by kind of delving too much in it, but the handout does a pretty good job of talking you through what you're doing. But it's kind of a neat way to think about it. That's how the GPS, the MapQuest, and things like that are working. Is you're at a site, you have a goal, and you have this information that you're trying to guide that search, and you're going to use heuristics about what appears to be the kind of optimal path to kind of pick that and go with it and see where it leads you. So that will be your task for the next week. What we'll talk about on Friday is caching.